Can you see
Very
it?
good. So we can all see your screen. So it's a pleasure to have Filippo that will talk about the holographic swan plant. Please.
Okay, well, first of all, thanks for having me here in this very nice workshop. Now, today I'll be talking about the holographic swan plant. This is mainly based on this paper here in collaboration with my supervisor, Joe Conlon. As it says, the main topic of this talk is to try and see whether swan plant constraints on 4D effective theories from a string origin can be mapped through the SCFT to either some sort of CFT inconsistency, or in case this is not possible, to CFT reformulation. And but the reason why I think this is an interesting problem is that many of these stringy Valve constructions rely on various different moving parts and various approximations, some of which are not often well established. There's various debates in the literature about this, so it'll be interesting to develop some sort of alternative framework, whether to ask the same questions and see if these theories are consistent or not. And well, more even motivation is also that perhaps the bootstrap project has been very successful in doing this, so in carving out the space of allowed physical theories in various contexts. So it'll be interesting to see if the same can be carried out in the context of the swamp and using these tools from the bootstrap. So when approaching a problem such as one that we just outlined, there are different possibilities. For example, in this context here, there are two. I will only mention one in this talk, but I'll talk about one in this talk, but I will also mention the other one for completeness. So one possibility is to start from, for example, a very simple example that we'll do here in the case of the LVS. So we'll start from a CFT, which is very simple to analyze, and then see if this can motivate a conjecture on CFT quantities, and then perhaps apply to other examples. In this particular case, we'll find that this prompts us to formulate a conjecture which is very similar to known bounds, so known positivity bounds in CFTs, but actually not quite. And on the other hand, one can actually start from the the well-established and the rigorous CFT bounds and see if those have any consequences. This kind of mirrors the distinction which one often encounters in the context of the swan plan. So often one has conjectures which are rigorous and well-proven, but don't have many useful information for low energy physics. And on the other hand, one can have, such we'll do here on the left-hand side, conjectures which are perhaps less well motivated, but more useful to obtain information about low energy physics. Sorry, my screen seems to be blocked.
Maybe you should try to, okay, seems now it works.
Okay. Okay, so of course we'll begin with holographic CFTs, and well, Julia did a bit of introduction, so I can skip some parts. So this theory will be characterized by an expansion parameter, which is always denoted by n in analogy with large n theories, although this is not necessarily the case always. And importantly, these are characterized by a large gap in the spectrum. So this means that we'll have an isolated subsector, which is separated by the rest by a large gap in chromal dimensions. And so at low chromal dimension, we only consider a finite number of single trace primaries, and there are corresponding double trace operators, so composed out of the single trace in this way here. And in particular, an important distinction will be between the operators made out of identical double trace operators and different ones. And of course, it will be characterized by, well, like from a dimension there, anomalous dimension. And again, this is, sorry, this is, okay. Again, then in these, well, this isn't the CFT data, which is actually used in the context of the bootstrap, and then one can write down this equation here, expand this correlator in terms of conformal blocks. And well, if this is done in a different channel, one gets the famous bootstrap equation, which basically amounts to requiring crossing symmetry. Now, one first observation is that in this context, crossing symmetry alone does not impose any useful constraints. And simply because with these theories on ADS, so solutions to the bootstrap equations at order 1 over n squared map 1-to-1 to all the possible linear independent quartic vertices that one could write. So this doesn't really give us anything. And if we actually want to constrain these theories, we would like to want something more. And this something more is given by the CFT positivity bounds, at least it's a possibility. So to cut the story short, well, under some assumption, which I'll skip now here. So the anomalous dimensions gamma 0L for identical double trace operators made out of identical scalars have to be convex and negative for spins higher than 2. And this was proven both in the context of the analytical bootstrap and also using the inversion formula of Coronhood. And also was proven in, well, different ways using causality arguments in a CFT, for example. And now this is a very simple interpretation of ADS. It just, for example, gamma 02 requiring gamma 02 to be negative simply means that this interaction, G greater than 5 to the 4th, must have a positive coefficient on ADS. So it's really the kind of thing we're looking for. We can try now see if we can apply to interesting scenarios. So LVS is a type 2B flux compactification, and all the moduli are stabilized at an exponentially large value of the volume. And this is one very useful feature because we can use this infinite volume limit to parametrically decouple all the heavy states in theory from this low line subsector we mentioned just before. And so we can, for example, in this case, if we send the volume to infinity, only a finite number of fields retain a finite formal dimension. And these are also assume universal values. And these are the graviton, which is always there, then the volume modulus and its corresponding axion. And the rest has a diverging conformal dimension, so it can be integrated out. And more precisely, this theory is also uniquely determined. This infinite volume limit is a well-defined limit, and all the interactions are fixed. And now one can start asking questions with having this simple playground at our disposal. So, for example, from the point of view of low energy effective theories, one could try and ask and see if, for example, modifying any of these coefficients by an order one parameter could be thought of something innocent and consistent. But if we know what the structure behind this is, we know that some modifications are actually not allowed. For example, if we look at the second equation, if we imagine to change all these minus signs here to a plus, then this looks like an innocent modification in the IR. But from somebody who knows the origin risk Lagrangian, we see that this corresponds exactly to changing the sign in the axion connecting term. And since phi is proportional to the log of the volume, this is equivalent to having a divergent axial decay constant in the infinite volume limit, which is totally inconsistent with string theory. So the question we ask now is, does this behavior show up in a CFT? Does this make anything consistent in the CFT? So, of course, as I was mentioning, the positivity bounds, we can start from there. But however, the naive positivity bounds, the one that I cited before, actually don't apply, and essentially for two reasons. One reason is that contact diagrams only modify the anomalous dimension up to a finite number of, up to finite L, essentially, given by the number of derivatives present in the interaction. Here we will have two derivatives, we have, so we will get spin 1, but the constraints only apply for spin height and 2. So this is quite unfortunate. On the other hand, exchange diagrams always give a negative contribution, which is simply because the corresponding Witten diagram always has two identical factors of the coupling appearing. So this will be always proportional to minus some coupling squared. So what we do claim is, however, that a very similar condition, which is not proven from the C point of view, and we suspect shouldn't hold in general, is that the mixed anomalous dimension, so the anomalous dimension of double trace operators composed of, for example, a volume modulus and an axion, actually these seem to correlate with one-plot conditions. And so we can see why, for example, with the example of LVS here, this is the anomalous dimension in the large L limit, where computations are simpler, and G mu are simply the coefficients of the two cubic terms. These give the leading order contributions. So with the LVS couplings, this is negative. And we see that if we switch the sign corresponding to the axion connected term, so we switch the sign of mu, then this anomalous dimension becomes positive, consistent with what we were saying. So reproducing the behavior we want to reproduce. And we can also notice that, so in LVS, for example, delta phi is fixed, but we can try and vary it now and see what happens. So here on the right is a plot of the sign of delta, the sign of gamma 0 as a function of delta phi. So for values smaller than 6, this corresponds to a potential that grows very fast, so parametrically faster than the string scale to the fourth, as in the large volume limit. And so this looks inconsistent, and this is excluded. And also the region between 6 and 8 is excluded. Now, we don't really have an interpretation for this, but I think it's interesting to notice that this means that the infinite volume limit of LVS lies precisely at the boundary of this region, so as indicated by the arrow, because the delta phi is 8.03 something. And this phenomenon is something that has been seen before, for example, in the context of the bootstrap, because many of interesting theories in the case of the analytical bootstrap were found to reside at special points of in parameter space, exactly very close to the boundary of the allowed region. So this is interesting to see the same behavior here. Okay, well now, of course, this is just one example. It doesn't make a conjecture. So we've looked at others. Let me just mention a few. So one example that's similar to LVS is perturbed stabilization, where there's two different competing volume effects in the potential. And again, for realistic values of the parameters, we get a negative anomalous dimension, and we have the same feature as in LVS, that we have this sign flip if we change the sign of the axion connected term. And other examples are perhaps more interesting, KKLT and or racetrack stabilization. Again, very similar. All of these before uplifting, of course. So still ADS vacua. And again, here we have this anomalous dimension is negative, precisely in the regime of validity of these series. For example, where single instant approximations can be trusted. And these are actually a bit different from LVS, because there's from a qualitative point of view, in this case, the axion is massive and there's a potential. So for example, we have a sigma a squared term in the potential, and it's precisely this term that gives the negative anomalous dimension. Finally, one last thing we've seen is a connection to the distance conjecture. So we've so far ignored all the heavy modes. We can sort of try and consider them and reintegrate them back, maybe one by one. And so consider the correlation function between two heavy modes psi and the volume modulus. Now, the dependence of the the Lagrangian containing the interaction between this volume modulus and this heavy field can actually, only depends on the Kähler module on K psi psi bar, which can be, and the volume dependence on K can be worked out by knowing the dependence of the mass of the states on the volume. And so one can actually compute these correlation functions. And well, now here, this will depend on one factor, which just depends on the LVS volume, the 3-point function LVS, and one function here, which is the 3-point function f phi psi psi. For example, we see that this is positive in the case of KK modes, giving a negative anomalous dimension. And more precisely, we could ask when this quantity here changes sign. And we see that this quantity here changes sign exactly when the dependence of K on V is such that the mass of these heavy states remains constant in the large volume limit. So said otherwise, a negative anomalous dimension in this context is equivalent to requiring heavy states to become light in the large volume limit, which is essentially the statement of the distance conjecture. Okay, so time is running out, so let me finish. So we've seen our CFT techniques, and well, we hope they can offer a promising tool to address these stringy ADS CFTs. And we've seen in particular that the sign of this mixed anomalous dimension, at least in some cases, seems to correlate with the known one conditions in various examples. And also it seems to be a connection with the distance conjecture. Now, I haven't had much time to talk about this, but of course, we don't expect this to hold in general. All the examples we've seen, this applies to the volume modulus, and this also applies to other examples that are still work in progress. And so let me finish by saying this is still very speculative and conjecture, but we hope that maybe more progress in these things would actually, the long-term goal would be to enable us one day to use this relationship in the other direction and use CFT bounds to actually navigate and map the swampland. Okay, I think this is it. Thank you for your attention.
Thank you very much, Filippo, for the nice talk. Is there any question for Filippo?
Massimo, can I ask one?
Yes, please, Michele.
So this is Michele Ciccoli. Hi. So, so did I understand correctly that you were saying that, so these LVS models are quite, I mean, they're okay, but they are quite close to the bound where the CFT is not valid anymore. The putative CFT dual, right?
Yes, they're close to the bound where the anomalous dimension changes sign. So
yeah, exactly. But I want to ask you, because you had this plot, and what does close mean, or very close? In what sense? Because you were showing this plot where you were plotting, I think, the field, your field. No, what were you plotting here on the axis?
So here on the y-axis is the sign of the anomalous dimension.
Right. I mean on the x-axis.
Yes, on the y-axis, and on the x-axis is delta phi, the conformal dimension of the volume modulus, so corresponding to the mass. Okay, right.
So when you say very close, what do you mean? How can you quantify this closeness?
So we have in this plot here the sign changes at 8, so when delta phi equals 8, and in LVS delta phi is 8.03 something when V is infinite.
Okay.
Actually, one thing we've tried so this is actually holds in the infinite volume limit. One thing we try to see is, for example, if V is finite, delta phi can be lower than 8. But in that case, there could be subleading corrections in the Kähler potential. So instead of having something 1 over V, we would have 1 over V squared corrections, and then these would actually allow one to come back into the allowed region.
But when you say large volume limit, it means that you are only focusing on some operators.
Mm-hmm. Yes.
Okay. Thank you.
Is there any other question? So basically, anyway, in all the examples so far that you have analyzed, things are still, so you haven't found any contradiction with the bootstrap. So all the examples so far lie in regions that are allowed. But yes, the type of constraints that have been used are just these positivity constraints for the anomalous dimensions, right?
Yeah, but these constraints are not proven in general. So it's actually all the examples I cited work. There are some examples I didn't cite where, for example, the anomalous dimension, all the ones involved with the volume modulus seem to hold, but in other cases, more exotic cases, for example, in fiber cases, when one has more axions, the ones between different axions, actually, they're all positive. So
I see.
This appears to be, probably, I don't really think it holds in for any anomalous dimension, but probably for a subset of operators.
I see.